In this video, I'm going to talk a bit about how quantum mechanics helps us build the periodic table, or at least how quantum mechanics determines how the periodic table ought to be built. And so the first thing I'm going to start off with is what's called electron shielding. And so the basic idea for this is that electrons closer to the nucleus are going to shield some of that positive charge from electrons further out from the nucleus. And so the electrons further out are going to have what's called the effective charge that it feels from the nucleus, which is determined by what we'll look at here in a little bit called Slaters Rules. And so what you see on the right here, so this is the radial equation for the 1s, the 2s, and the 2p orbitals. And so we can see on the x-axis is the distance from the nucleus, where right here at the 0 would be where the nucleus is. And then here is the electron probability on the y-axis. And so you see that the 1s orbital is very close, and most of its probability distribution is much closer. So it's going to shield the 2s and the 2p orbitals. And I actually have this on the saved on the Desmos calculator here. So this is just the same thing. So in the red is the 1s orbital. In the blue here is the 2s orbital. And then the purple here is the 2p orbital. And so we see, like I said, the 1s here in red is shielding the other two. The 2s here in blue, it looks like it's further away than the p orbital. There's a lot of overlap, but it also has this little bit down here, this little spike down here that's going to help shield it. And so we can add some of the other orbitals here. So we'll add here the 3s. And so we see that this, most of its distribution is much further away. And so that is going to be shielded by all of these, where then we can add the 3p. And so we have this also being shielded. But the 3s has this little bit of distribution here, which is helping to shield some of that. And then we can actually add the 3d orbital. And so we see that this is right here. And so this is going to be shielded by everything down here. And I will leave a link to this saved one here in the lecture notes, which will be linked to in the description down below. So if you wanted to play around with this. So these ones down here where it has the S, SP, SP, and D are the actual radial equations for the probability distribution, where up here, these ones that have R, these are the probability amplitudes for these. And so these actually show this. So, and these ones actually go out down into the negative because before you square them, which is what's going on with these ones down here, they're squared. And so that's why they're the probability distribution, where the ones up here are the probability amplitude. But that's sort of beside the point here. But like I said, the takeaway from this is that these closer orbitals are going to shield the further away ones. And so then the question is, how do you determine how much positive charge an electron will actually experience from the nucleus? And so that is where we come to Slaters rules. And so this Z star here is the effective charge that it's feeling from the nucleus. This Z is the actual number of protons in the nucleus, which each one is a positive 1 charge. And then we subtract this S, where this S is sort of the amount of shielding that it is experiencing. And so these are the rules here called Slaters rules. And so the electrons are grouped like this. So the 1s, the 2s, and the 2p are together, the 3s and 3p, the 3d by itself. So then the 4s and 4p, 4d, 4f, 5s, 5p, and so on. And so electrons in higher groups do not shield electrons in lower groups. So, for instance, if we want to look at the shielding that like a 4s electron feels, we would only consider this group, this group, this group, this group, and this group, even if there were higher groups for it. And then so for the s and p orbitals, we follow these rule 3 here. So rule 3a, 3b, and 3c, whereas if we are looking at a d or an f orbital, then we would follow this rule 4 here. And so this tells you what you would actually put in for s here. So that's what these numbers are. And we see that a lot of them are lower than 1, and so there is still going to be some positive charge getting through, and so that's what we can look at here. So a few examples. So this one is already worked, and so for oxygen, if we wanted to look at what we are experiencing for like a 2p orbital, so we have 8 here, so the number of protons that oxygen has. So I have this over here is 8. So we take the number of protons that has, and then we want to subtract off based on these rules. And so this 2 times 0.85 is because of rule 3b right here, and so that is taking this 1s2 into account. So that's why there is 2 of them times this 0.85, and then this 5 here is because there is 4 plus 2 is 6, but we're looking at one of the electrons in this group here, and so we only have to consider 5 other ones in addition to this proton, or the electrons in that group. And so that is the 0.35, which comes from 3a, so right here. And so it ends up being a total of 4.55. So there are 8 protons in the nucleus, but a 2p electron is only feeling the force or the potential of about 4.55 protons because of the other ones, the other electrons shielding it. And so we can look at another example here. And so we're going to look at nickel. And so for nickel, we can look at a 3d electron and a 4s electron. So this is the 3d, this is the 4s. And so nickel has a number of protons is right here, so it has 28 total protons. So we can go over here, and so if we want to look at a 3D one, so we take our 28, then we want to subtract, and so we're looking at d electrons. So we want to look up here, and we know that that rule 4 is for d electrons, and so we first want to look at a, so the number of electrons that are in the same d orbital will have 0.35, and so we see here that there are 7 other ones in the same d orbital, and so we will actually have 7 times 0.35, because there are 8 here, but we're actually looking at one of them, so there are only 7 other additional ones. And then we want to subtract off, so we look at rule 4b, so electrons in any lower groups get a 1. And so there are 18 electrons in the lower group, so there are 8 plus 8, which is 16, 17, 18. And so we have 18 times 1.00. And so what we end up getting for our Z star is it will actually be 7.55. And so there are 28 protons, but this 3D electron is feeling the force that's equivalent to 7.55 protons. And then so if we want to look at a 4s electron, so that's actually looking at another group higher up here. So we still have our 28 protons, but now we're looking at s electrons. So we want to look at rule 3 up here. And so for rule 3a, so electrons in the same s orbital will have 0.35. Well, this has 2 electrons in the 4s orbital, and so we're only looking at one other one, so it'll just be 1 times 0.35. Then we want to subtract off, so let's go back up and look at rule 3b. So electrons in the n-1 contribute 0.85. So how many electrons are in the n-1? And so we see that that is 8 plus 8 here, so that is actually 16. So it would be 16 times 0.85, and then what we have for B here, so, or 3C rather, is n-2. So anything lower than that is just going to have a 1. So each electron lower than that is going to block out the equivalent of 1 proton. And so what we have here is we have 8 and then 9, 10. So minus 10 times 1.00, and so Z star for this will actually be 4.05. And so we see that electrons here in this further out shell are feeling a lot less of those protons than one that is inside, and that is because the ones further out are actually being blocked by these ones that are further on the inside here. And so that is how you actually apply those rules. And so I wanted to look at this as well. So copper, which is the next one over. So copper is number 29. So if we just add one more proton and one more electron to it, and we want to look at a 4s electron for this. So this has an additional 3d. So this is 3d8. This has 3d9. And so we're adding another proton, but we're also adding another electron to shield it. But we see that this has an effective proton charge of 4.2, which is higher than the 4.05. And so this is actually important for a lot of what are called periodic trends. And so I actually have that down here. So if we look at the periodic table, we look at the periodic trends, what you see is the atomic radius, which is these ones here in pink, actually gets larger as you go down and as you go to the left, which seems a little bit counterintuitive because you're adding more electrons as you go from left to right. So you'd think the atomic radius would get larger as you go left to right, but the atomic radius is actually getting smaller, and that's because the electrons, when you add another proton, are feeling a little bit more of that Z effective because the extra electron doesn't block as much of the positive charge as a complete proton. So you get the +1 from the proton, but you only get minus 0.35 or so, or 0.85 rather, from the extra electron. And so you are actually increasing the amount of positive charge that every electron feels as you go from left to right on here. And so that actually sort of pulls the electrons in even more, reducing the radius. And you can see too also with the ionization energy, if there's more positive charge, it's going to take more energy to remove an electron. Electronegativity, so that's in like a molecule, like an atom sort of pulls electrons to it. If there's more positive charge, it's going to pull electrons to it, so more electronegativity. And then same with electron affinity. And so, that's why like the halogens in this column here are often with a -1 charge, because that that sort of extra positive effective charge is allowing it to sort of accommodate more of that negative charge, where over here you're going to have sort of, less positive charge, for the number of electrons you have, and so those ones are actually going to uh, lose electrons much easier. And so you can see how this shielding here is actually sort of what determines these periodic trends. And so, a lot of these periodic trends can be explained by this whole shielding phenomena that I've been talking about here, where electrons in these lower shells are shielding some of the positive charge from reaching these electrons in the outer shells. And so we will look at a few other things that sort of determine where electrons go, sort of in the orbitals of an atom. And so the next thing to think about is what's called the Coulombic energy of repulsion, which is this capital pi C, in the exchange energy, which is this capital pi E. And so we see that if we have some p orbitals right here, and say there are 2 electrons that go into the p orbitals, so it's higher energy to have both of them in the same orbital, but then, in this singlet coupled state with opposite spins, which is so that's, a necessary thing. But this is a higher energy state than if one of these electrons goes to a different orbital. So that is because of this Coulombic energy of repulsion. The electrons are going to want to be in different spatial regions, and so this has the spatial symmetry here, but that causes them to be closer together, which is higher energy, and so it's actually going to want to separate these. But then we have this exchange energy, and so if both of them are in the upspin, or if both of them are the downspin, the take-home message is that both of them are in the same spin. That's even lower energy, and so this is called exchange because you can sort of exchange these electrons back and forth, and so that actually increases the total entropy and therefore is favorable. And so this leads to what's called Hunds rules, which is this, where the electrons are going to want to go into separate orbitals with the same spin, because that's going to be much more likely because it's less energetic. So, in things like thermodynamics and things like that, states in chemistry and physics are always trying to go to the lowest energy state. And so that's kind of the rule of thumb, is that things always want to go to the lower energy state. But then we have this here, which increases the energy because we don't have that entropy of the exchange, of the loss of the exchange energy there. And then here is even less likely because we now are pairing them up, which is even more energetic. And so that is what's known as Hund's rule, where the electrons actually want to be in different orbitals but with the same spin. And so we can look at the total pairing energy. So this uppercase pi is just the uppercase pi sub c, which is the Coulombic repulsion, and then the uppercase pi sub e, which is that exchange energy, where the Coulombic energy is positive because, remember, in electrostatics, positive means repulsion, negative means attraction. But the exchange energy is negative, and so if we have this exchange energy here, we're actually reducing the energy of our system and making it more likely. So for energy levels, this energy tends to be smaller than the difference in energy levels designated by the quantum number n. But once we get up to the 4s and 3d level, then it's the 4s that fills before the 3d. And so we can see that here, where the 2s here is higher than the 1s, but then the 2p is even higher than the 3s, than the 3p. But now we see that the 3d is actually higher than the 4s. So it's actually going to fill in the 4s before it starts filling in the 3D. And this is because the energy going from n equals 3 to n equals 4 at this point is actually less than the energy of the Coulombic repulsion plus the exchange energy. And we see that this is for L greater than or equal to 2. And so this actually explains another thing we see on the periodic table, which is why these ones here are filled in first, because the 4s get filled in first. And so we see here on the top the H, the hydrogen has 1s1, the helium has 1s2, then lithium has 2s1, then beryllium 2s2, then we go through the 2p's over here. Then we go to the 3s and the 3s1 and 3s2, then the 3p's. But instead of going to right to the 3d's here, we first have the 4s one right here and the 4s2 right here before we start filling in these 3d orbitals right there. And so this is another thing, this energy difference between the Coulombic energy of repulsion and the exchange energy actually is another thing that sort of determines what shape the periodic table must take, because this 3D is actually higher energy than the 4S. And so those will fill in faster. But what you actually find too then is that once you start putting in these 3D, those 3D start shielding the 4S. And so when you start actually filling these orbitals, the 4S then moves to a higher energy. And so that's why the 4s electrons are the valence shell electrons and are the ones that get lost. So when you have like an oxidized metal, it's actually losing its 4s electrons if it's in that group. And so, yeah, that is Hunds rules. And so if we kind of put all that together, we get what is called the Offbow Principle. And so it follows these three rules. So the first one is that electrons placed in lowest energy levels first. So that's just kind of a general rule in, chemistry and physics, that things prefer lower energy levels to higher energy levels. Then we have the Pauli exclusion principle, which I talked about in a previous video. And so every electron must have its own set of quantum numbers. And then the Hunds rule of multiplicity, which is what I was talking about above. And so it says to maximize spin. And by that it means, we want these to be either both spin up or both spin down. We don't want the up canceling out the down here, and so it maximizes spin. And so then we can start filling in the electrons into our atoms here. So we see here we have the hydrogen and it has 1s, then the helium has 2s2, then we start, or 1s2 rather, then the lithium we start filling in the 2s. Then after we get to the boron, we start filling in the 2p, and these want to fill in, so we start with just the 2 here, then there's 2 here, and then we have these that are all 3 the same spin, and only once we have filled those in do we start coupling them up like that. And so if you've ever taken a chemistry class, you've probably seen something that looks like this, where at n equals 1 we start with the 1s, Then we go down to n equals 2 and we fill in the 2s and then the 2p, and we just follow this sort of winding line going through here, where the yellow ones are where L equals 0, the blue are where L equals 1, the purple L equals 2, and the green is L equals 3. And so that is how you actually fill in the electrons into the atom. So that gives you the electron configuration of atoms. And so one way that I always like to think about the Offbow principle is as the sort of bus seating principle. So if you've ever taken like a city bus before, which I definitely have, so you see a bus like this, and so it's an empty bus. It stops, it picks up a passenger. That passenger will take this seat, the next one will take this seat, then the next one will take this seat, then this seat, and so on and so forth. So everybody is taking their own pair of seats, and only once every one of these has been taken will the next person then start actually sitting next to other people here. And so that's kind of the same thing with our Offbow principle, as we keep filling these seats, and only once every pair of seats has one person in it will other people start sitting in the second seat, because everybody on the bus always wants to, sit with as much room as they possibly can. And so that's kind of the way I like to think about it, as this sort of, sitting on the bus principle. And so that's kind of, I guess, the Hunds rule principle there. It fits with Hund's rule very well, where each of these orbitals is going to be filled by a single electron before you start actually pairing them up. But anyway, I hope you found this video helpful, and I hope you were able to see why quantum mechanics is what determines how the periodic table is actually built. That, the shape of the periodic table here isn't something that's arbitrary. It's built this way for a reason, and that reason is determined by quantum mechanics. And similarly, the periodic trends that we see can be explained by quantum mechanics, and in particular the shielding of the electrons from the positive charge in the nucleus. And once again, I'll just repeat, all this stuff will be linked to in the lecture notes and the description down below. So if you wanted to look at this stuff a little bit slower and on your own, then I would definitely recommend checking that out. And I will see you in the next video.